Hello, this is Dr. Armand again, bringing you the last lab lecture of the semester. I know some of y'all are excited, cheering that this is the last lab lecture. Uh, Today, I like to wear my alma mater, Clemson University. Go Tigers! I'm wearing a tiger orange T-shirt, a tiger orange polo today. So again, Clemson was where I went to graduate school. Back then, though, their football team wasn't that great. But I did like the school. It's a good school. You should visit it sometime. Clemson University in South Carolina. And I'm wearing their tiger orange polo today. Uh, so on that note, we'll get started with today's lecture. Another lecture about using Beer's law to determine the concentration of a particular ingredient in a mixture. So we'll get started with that today. It won't be a long lecture today. It's a pretty short one. Okay. So, as you're quite aware, experiment 9, we were determining the concentration of food dyes in different solutions, and in lab you would have determined it in different beverages. You learned about Beer's law and how to make dilutions and whatnot. Experiment 10 would have been a little bit different. We're looking at determining the amount of phosphoric acid in soft drinks. So most soft drinks contain phosphoric acid. If you look at a can of Coca-Cola or Pepsi, you look on the back of it, one of the ingredients is phosphoric acid. And the sad face is because this is the last lab lecture. So, what's unique about phosphoric acid? Well, of course, it's an acid. It's actually a triprotic acid because it has 3 hydrogens. So we call this a triprotic acid. So again, it's referred to as a triprotic acid. And again, tri meaning 3, protic meaning hydrogen ions. So it has 3 hydrogen ions that it can disassociate. And again, it's commonly found in soft drinks. Pretty much any soft drink you can look at, with the exception of maybe Sprite and 7-Up. Those colorless soft drinks typically contain the like the ones like Coca-Cola, Pepsi, Sam's Cola, HEB Cola. They have phosphoric acid. Now, one interesting thing about phosphoric acid, as you should know, is that it's colorless. And if it's colorless, what that means is that we cannot use the spectrometer, the UV vis spectrometer, or the visible spectrometer, I should say, for this experiment. Because remember, for visible spectrometers or spectrophotometers, you have to have a color solution. So obviously, phosphoric acid is not color, it's colorless. So that presents a problem when we want to determine the concentration of phosphoric acid in soft drinks using Beer's law. One of the reasons that phosphoric acid is added to soft drinks is to give it some tartness. So that's why it's added. And you may say, well, phosphoric acid is an acid, and we just got done doing in experiment 8 doing acid-base titration. Why can't we just simply do an acid-base titration to determine the amount of phosphoric acid in the drink? And that's a good argument, but the problem with that is that in most sodas we have multiple acids in it. So citric acid, carbonic acid, these are acids that are commonly found in soft drinks. Carbonic acid is probably most commonly found in soft drinks because it gives it its carbonated effect. The carbonated water is carbon dioxide dissolved in water, which is carbonic acid. So they use carbonic acid to give it its bubbly appearance. This is citric acid down here, and citric acid is another triprotic acid. It has 3 acidic protons on it. So since there's a mixture of acids in the cola, we can't just simply do an acid-base titration. So this again is a citric acid is a triprotic acid. So again, triprotic means it has 3 acidic hydrogens. So hydrogen there, it has to be a hydrogen on a very electronegative. Oh, not that one, my bad. Oop, oop. Let's back it up. On a very electronegative element. This one here is not a acidic proton. And you'll learn why when you get into organic chem, where you take Gen Chem 2 with Dr. Armand. Dr. Armand discusses this stuff in Gen Chem 2. Okay, let's move along. So the obvious question is, what can we do to make phosphoric acid have a little color in it so we can use the visible spectrometer? And that's a good question. So what we're going to do is we're going to add something, and you're going to love this word because we used it a lot early on. We're going to add a metal or a transition metal complex to it to give it some color. Let's just kind of recap on transition metal complexes. And as we learned in experiment 5 with the saccharinate, a complex ion or transition metal complex is when we have a central metal ion that's positively charged and it's covalently bonded or interacting, coordinating to 2 or more anions or molecules, which are ligands. So ligands can again be anions or molecules. Those make up ligands. And what's important about molecules and anions and ligands is that they have an accessible lone pair of electrons. And what do we mean by accessible? Accessible means like a lone pair of electrons on a nitrogen atom or single bond oxygen atom. And what do we mean by single bond oxygen atom? This is an oxygen atom that has a negative charge. So for example, NH3, if I was to draw NH3, and you'll learn how to draw this in actually the next chapter you're taking Gen Chem 1. It has an accessible lone pair of electrons. So that's why NH3, it can be a ligand. Or any kind of amine can be a ligand, as long as it has an accessible lone pair of electrons. Now another one we can use, of course, we talked about is water. I apologize for my artwork. And water has 2 accessible lone pairs of electrons. So water can be a ligand. Water, ammonia, anions, chloride, fluoride, bromide, these all can be ligands. Now, for example, what I mean by single bond oxygen is if we have an anion that has, for example, a deprotonated acid, single bond oxygen atom. 1 second. So for example, if I drew the acetic acetate, so this is the acetate ion. Typically, metals prefer the single bond oxygen atom for coordination because it's really easy to access these lone pairs because this oxygen is negative charge. Whereas this oxygen, the double bond is zero charge. It has no charge. And of course, yes, that oxygen does have lone pairs, and in some instances, the double bond oxygen can coordinate it, but the one it likes the most, the metal likes the most, is this negatively charged oxygen. And anytime you see an oxygen with just a single bond to it, it's going to be negative charge, so nothing else attached to it. These are all examples of what's it called? All examples of ligands. Now, when you mix these ligands with a transition metal, then the good stuff starts to happen, because transition metals are what? They're D block elements. And in gas phase, we learn about the D block. It's, D block, the D orbital, we say has 5 degenerate orbitals. And then the electrons occupy these degenerate orbitals. But what we're going to show on the next slide is going to really blow your mind. But just remember, in the gas phase, what you learned in lecture just a week ago, D orbital has 5 degenerate orbitals. That's in the gas phase. What we're going to talk about is, why do transition metals give you colored solutions? If all the orbitals are degenerate, something must happen in solution. So when you're in the solution phase, it changes up the orbital mixture. And so what I want to show you here is that here we have cobalt with 4 chlorides. It's the characteristic blue solution. So cobalt tetrachloride, cobalt tetrachloride anion is blue when it has 4 things coordinated to it. But when you look, for example, here, we change the ligand. We changed cobalt's ligand to water. Now we have 6 waters around the cobalt. The solution changes color. And as we'll see on the next slide, when you change the anions or the ligand, you change the energy associated with that coordination. And we'll talk about that in just a second. For example, here we have copper and water with 6 waters. That looks ugly. Let me undo that. So copper has 6 waters. Hexa aqua copper gives you that characteristic light blue color that we always talk about. That's the characteristic color of copper, because when you put copper in water, it forms copper hexa aqua cation. But then when we change copper's anion, or change copper's ligand to a chloride, you see it changes it to a yellow color. So what I'm trying to show you here is that when you change the ligands, you change the interactions between the ligand and the metal. And if you kind of like this stuff, this stuff we're talking about, this is what you learn in inorganic chemistry. So for example, nickel 2 plus usually is hexa aqua nickel 2 plus, gives you the characteristic green color. However, if you change the waters to ammonia, now we have nickel hexaamine, you get a characteristic blue color, because again, the electronics or the interactions between the ligand and the metal are changing. So why does it change? And it changes for a variety of reasons. One could be the different oxidation states of the metal. So for example, for vanadium, when it's +2, it's a purple solution. When it's in +3, it's green. +4 is blue, and then +5, it's yellow. For chromium's 3 major states, +2 is purple, +3 is green, +6 is yellow. Now remember what we learned in last lecture. The color it appears is different from the color it absorbs. So if something appears at a low wavelength, it's going to absorb at a high wavelength. If something absorbs color at a high wavelength, that photon at that higher wavelength is lower energy than the photon at the lower wavelength. So I don't know how I can write that. So again, the color absorbed is opposite the color it appears as. So again, chromium, very common example. Chromium plus chromium -3 is the dark green. Chromium hexaaqua is +3. Chromium hexaamine +3 is like a purple, darker purple. Same thing with cobalt. Cobalt hexaaqua cation is pink. Chromium hexaaqua is cation is purple. So just by changing the metal, we change the type of photon that's being absorbed. And so again, the absorbed color is the color when the electron absorbs that energy to move to a higher energy level. And so if something appears blue-green, it's going to absorb red. So here we're having, as we go up, we're increasing lambda. So if we increase lambda, then we increase lambda, energy decreases. As we go down, wavelength decreases and energy increases. Because remember, they're inversely related. So if something appears yellow, it's going to absorb a blue photon of light. And that's a very energetic photon in the visible region because it's a very small wavelength. If something appears purple, it's going to absorb a less energetic photon in the yellow-green region. So it'll be yellow-green photon. So the absorbed color tells you the strength of the interaction between the ligand and the metal. So if something absorbs a violet photon, it's going to be a very strong interaction. And the reason this occurs is because in the solution phase, the d orbitals split. And how do they split? They split into 2 to 3. So what does that mean? We have 2 higher orbitals and 3 lower orbitals. The higher orbitals are referred to as Eg, and the lower ones are T2G. And so what happens is when a photon in the T2, when an electron in the T2G orbital, such as here, absorbs a particular color of light, it jumps to the next energy level. So here, this photon absorbed the yellow-green light, it moves to the next energy level. And since it absorbed that yellow-green light, it's going to appear purple. So its absorbance would have a lambda max near the yellow-green region of the visible spectrum, and it would appear purple. So again, light comes through. This electron here absorbs yellow-green light. It moves to the higher d orbital states. So it's absorbing the yellow-green light. It allows all the other light to pass through. That's why the solution appears purple. So the higher d orbital state is e.g., the lower d orbital state is T2G. So an electron moves from T2G to EG. And that's where you get these colorful solutions for transition metals, because you're always moving an electron from a lower energy level to a higher energy level. Now let me show you something here. Zinc. So say zinc 2 plus, as you learn in lecture, zinc 2 plus, it's argon let me do that again. Argon 3D10. And zinc is characteristically colorless. So zinc 2 plus is colorless. And let me explain why right here. Why is zinc 2 plus colorless? Because if we draw the orbital diagram, so we have our EG, let me move that over here, my bad. And T2G. This is EG, T, 2G. And so for zinc 2 plus, so I'm over here now. I'm going to draw you the orbital diagram of zinc 2 plus. This is the 3D orbitals in solution state. So this is 3D in solution. We draw the orbital diagram, adhering to Hund's rule. And what do you notice about these 3D orbitals here in solution state? What do you notice that's different from the example we had at the bottom? That's right. What you notice is that this is completely filled d orbital. So there's no room for an electron to move to the higher d orbital state. And that is why zinc 2 plus solutions are colorless, because if you have a completely filled d orbital, you can't absorb a photon of visible light to move a lower d orbital electron to a higher d orbital electron. So again, let me explain this. So down here in this example, we only had one electron. When the light passes through, this one electron absorbs the yellow-green light and moves the electron to an empty EG orbital. Since it absorbed yellow-green, it's going to appear as purple because all the other colors that pass through give it the purple appearance. Now, with zinc 2 plus, its electron configuration is argon 3D10. And as I said, zinc 2 plus solutions are characteristically colorless. And the reason they're colorless, because if you look at their 3D orbital diagram in the solution state, you see that it contains a full d orbital. So there's no room for an electron in the T2G state to move to the EG state, because you only have two electrons in the orbital. And that's why zinc 2 plus, cadmium 2 plus solutions are colorless, because they have a completely filled d orbital. There's nowhere for the electrons to go from a lower d orbital to a higher d orbital. And if that's not cool, I don't know what is. That explains why zinc is colorless. And for example, cobalt is not colorless, because cobalt has room to go from a lower state to a higher state. It absorbs a photon of visible light. The electrons in cobalt's lower state moves to the higher state, and you get this color solution. And so this is why transition metals give you vibrant colors, because this transition, this movement of electron from a lower d orbital to a higher d orbital. So obviously what we're going to do to phosphoric acid is add some transition metal to it, or a transition metal complex, to give it some color. And so to determine the concentration of phosphoric acid, of course, phosphoric acid contains phosphates, and the unique thing about phosphates is that it complexes with a solution of ammonium molybdate and ammonium metavanadate. And when you take this ammonium molybdate and ammonium metavanadate, which are shown here, ammonium metavanadate, ammonium molybdate, when you mix it with phosphates, it forms, and this is a tongue twister, vanado molybdo phosphoric acid. And what's unique about this solution is it's yellow. So if it appears yellow, it's going to absorb in the blue region. Of the visible spectrum. So what we would do is, what we would see here is, if we had a solution of vanado molybdo phosphoric acid, you put it in the UV vis spectrometer, you're going to see a very strong absorption peak around the blue region of the visible spectrum. And vanado phosphoric acid, what happens is, the greater the concentration of phosphate leads to a more intense yellow solution. So the more phosphate you have, the more intense the yellow is, the more absorbance happens. So now now that we have some color to the solution, we can use the UV vis spectrometer and now do Beer's law, because now we have something that absorbs in the visible region. And this is what you would do with something that's colorless, and you want to do a Beer's law experiment with it. You need to find something that it interacts with to give it some color, so that you can study it in the visible region. And so what you would do is, you would prepare your standard of phosphate solution. You would add some of this ammonium molybdate, ammonium metavanadate. Based on the phosphate concentration, it would change it into, it would give it yellow color. So it would make it more yellow or less yellow depending on the concentration of phosphoric acid. So again, you would use Beer's law. The stock solution we would use in this case is potassium dihydrogen phosphate, 0.1 molar solution. You would prepare a series of standard solutions using a 25 ml volumetric flask. The lambda max for vanado molybdo phosphoric acid is 400 nanometers. And then from the standard solutions, you would create a Beer's law plot, which is absorbance versus concentration. Usually concentration is in molarity, but it could be in millimolar or micromolar as well. You would do a linear regression and you would get a chart. Then what you would do is, you would need to prepare your unknown. And so unlike the previous lab where your solution was already the same color that you were investigating, with sodas, you need to do two things, or there's two issues with sodas. First, you have to make sure all the gas is out of the soda, aka it's flat, because the bubbles will affect its absorbance. Secondly, is the caramel color means it's already going to absorb some in the at the lambda max. Since it's already a brown color, when you put it in the UV vis spectrometer, it's going to absorb some in that 400 nanometers. So we got to do two things to get rid of that effect of that absorbance. One is, you can take some of your unknown sample, diluted by like a factor of 50, and then you could run it, and that would minimize the effect of the absorbance of the soda. Secondly, you could take some soda as your blank. Like some of y'all, when you're doing experiment 9, your blank is water. You could blank with soda, and that would remove any background absorbance, and then you can add your molybdenum ammonium molybdate, ammonium metavanadate to the solution to give it a yellow color, and then run it again. So these are two options for preparing your unknowns. You can do a diluting, so you can dilute by a factor of 50. So for example, if the original concentration is, say, 0.8 molar, we take 1 milliliter of 0.8 molar and dilute it to 50 milliliters. This is a 50-fold dilution. So now the dilute solution would be 1/50th the original concentration. So that would be, it would be 0.016 molar. So that's how you do a dilution, diluting a sample by a factor of 50. So on that note, that concludes today's lecture on determining the concentration of phosphoric acid in sodas. Your alt experiment 10 uses Beer's law. It may not be sodas, but you do use Beer's law for an experiment. Also, just wanted to let you know that today is actually my birthday, so happy birthday to myself. April 15th, even though it is the usual tax day, it is my birthday. So that's why I gave you a short lecture today, because it's my birthday. On that note, I've enjoyed giving you lab lectures. I hope you enjoyed them too. And that concludes the lab lecture series for General Chemistry 1 lab. So on that note, Dr. Armand is signing off.